Michael Bernstein, who's my colleague at Stanford, assistant professor in computer science. He's a member of Human-Computer Interaction Group, and he works on crowdsourcing and thinking about how kind of large tasks can be boiled down into small tasks. He's also the co-author of the team who did the ImageNet, which is the big labeled data set of images. He designed the crowd working interface for labeling those images, and I'm really happy to have him here after being in car for about 2 hours.
Thanks. Thank you, Yuri. Yes, I think I'd like to salute 3 parties. First, Yuri and Pinterest for inviting me up here. Second, Chuck, the previous speaker, thank you, Chuck, for everything I didn't get to see. And third, I'd like to salute the 101 highway and crashes thereon, making it about a 2-hour commute from Stanford. All right, so let's talk about crowds, computation, and the future of work. So I'm really animated by this question of how groups of people can come together to tackle really hard goals. Pinterest is one example of an organization that's a group of people trying to work together toward hard goals. And whether it's crowdsourcing or organizations, this thing, it turns out, is really hard. There's an entire field. It's really bad when there's an entire field dedicated to telling you all the ways that we're very, very bad at organizing ourselves to try and tackle these goals. We're really good at splitting up work and really bad at planning how hard it's going to be to reintegrate it. You can think of software engineering projects you had in college, maybe as a reminder of that. We don't foresee the kinds of challenges we're going to have coordinating all sorts of challenges. And this is not unlike in the judgment decision-making psychology literature, how people make consistently biased and poor decisions individually. It's just a difficult challenge to think about how will we integrate a large number of people in a socio-technical system to produce exactly the desired effect, whether that would be data labeling like it would be for ImageNet or an organization like Pinterest. Now, where this field of organizational behavior sees nothing but problems, I see an opportunity because increasingly all of this is getting mediated by computation. And because it's mediated by a computer, it means that me as a designer, as someone who does human-computer interaction and interaction design, we can design that mediated channel to achieve the goals that we're interested in. So this is a huge opportunity from my point of view. Collaboration has sort of happened ad hoc, person to person from up until today, and all of a sudden now we have the opportunity to try and nudge us and design that channel to overcome those biases, those heuristics, those bad decisions that we make. Now, all of that opportunity has sort of boiled down to this point, to this. I would say it's a little bit underutilizing our human potential, but it's also very important for visual knowledge and many other things. What we do see is people creating crowdsourcing labeling interfaces like this that reach out to hundreds or thousands or tens of thousands of people to gather data. And this is fine, but it seems a little bit like less than what we might want. So my group has worked on this kind of stuff, as Yuri was gesturing toward. For one, I said, this is kind of, people are too worried about getting things wrong. What if we made this a little bit easier to get something wrong? So there's a little bit of audience participation here. Everyone sort of hold up your hands like this in front of you. Great, now clap. Good, okay, so that's what I'm gonna ask you to do. You're gonna see a series of images. Whenever you see a man on a motorcycle, clap. Ready? Here we go. Oh, you're doing great. Okay, put your hands down. Okay, so what you can tell is that this has become way harder. These images are going at about, I think, 150 milliseconds per image. But what you might have also noticed is that while you may have missed something, in general, there are patterns here. We're delayed and we're error prone, but we can model those delays and we can model those errors and show it to a few more people and get something like an order of magnitude increase in the labeling throughput with equal precision. So we're able to really massively scale up data collection by thinking more holistically about what people are interested in. Don't make them worried about making errors. Say it's okay to make a few errors. Just sort of go with the flow. We've scaled this from up to experts, where we can create these crowdsourcing workflows that can convene teams on demand. Here you can see sort of one of these workflows in the upper right, and an animated video that they make on the left. This was actually starring my colleague at Stanford, Terry Winograd. He's over on the right with the black hair. This is a group that I'd never met before, might never meet again, but On Demand has convened animators, voiceover artists, directors to produce something in about 24 hours from start to end. We're even writing short stories. This is on top of Mechanical Turk, so we call it Mechanical Novel, that uses these iterative loops of reflection and revision to try and actually reflect and say, hey, how should this story change to be better? Don't just try to identify typos, but actually say, how do we structure this story? We're talking about, what do workers need in these environments? Collective action. How do we help workers actually exert pressure back on the employers to actually have impact? So we're building those kinds of systems as well. But the more and more I did this kind of work, the more it just started to feel like we were getting into a bit of a rut. There's a sort of von Neumann architecture underlying all of this crowdsourcing work. This architecture is basically algorithmic, and basically what it's trying to do is modularize. So you take these big goals and you try to split them up into smaller goals and predefine everything. And the power of this is that then computation can decide, okay, we're going to route this there, we're going to get, replication of 3 over here, etc. They all look like this over on the right. I'm just citing a few papers, but they're all boxes and arrows and loops. The problem is that the kinds of things that you actually want to achieve, things like invention, production, engineering, they haven't been able to be achieved with these models. And it turns out that a lot of different literatures, it doesn't matter whether you're talking about this needing situated action or a reflective practitioner or requiring reciprocal interdependence, they're all just pointing out that these predefined workflows are fundamentally incompatible with complex work. So what are we going to do? Well, so far, not much. Some of the main thinkers in these spaces are basically acknowledging Wikipedia, for example, in the upper left, is limited in what it can do by what it can make modular. Linus Torvalds talks about how the Linux kernel depended on this modularity. If it weren't modular, they couldn't have done it. And then places like Topcoder actually advertise how they atomize things. But the problem is that this von Neumann architecture is essentially confining these crowds to goals that are just so simple they can be entirely predefined. So think of it. The only thing you can do using these techniques are things where you can write out a perfect recipe. And when was the last time that a project you were working on was something where you could write out a perfect recipe and it would run the first time? So what we've been pursuing recently has been essentially a different kind of architecture, structuring large groups much more like computationally infused organizations. So we take inspiration from what the organizational behavior literature knows about how people can collaborate and coordinate, and then essentially mix in a healthy dose of computation to do that. So I'm going to give a couple examples of this. The first is called Flash organizations. This is work done in collaboration with my colleague Melissa Valentine in management science, as well, and led by Daniela Ratelny, a PhD student. Basically, I want to make the point that this is powerful. Flash organizations are these rapidly assembled, reconfigurable organizations that you can bring together in just a moment's notice, composed of online collaborators. So just to sort of bang the point with you over the head, we're moving from a model that looks like this to something that looks much more like this. Well, not exactly like that, because that's what you work in today, something where there's actually really a computer in the middle. And what does that mean and afford? Well, to cut to the chase, we're able to convene these crowds, again, people who have never met before and might never meet again, to tackle these really open-ended complex goals like product design, software development, game production. And we're able to do that in part by creating software coordination techniques. We've been building this thing called Foundry in my group at Stanford that helps bring people together, coordinate them, and direct them. You should probably think that this is insane. It sort of is. Again, it shouldn't work. The reason it shouldn't work, the reason you're probably worried, is that organizational behavior says that people have to know each other in order to collaborate well. This is known as asset specificity in the literature. And it turns out that this isn't always the case. There are kinds of organizations like film crews and disaster response teams that are actually very effective at coordinating, even though the people there might not have worked together before. And the way they do it is through these things called role structures. Role structures are basically an indication of what our mutual roles are. So let's say Yuri is the director of a movie. and I'm the gaffer. Yuri and I may have never worked together before, but I know as a gaffer how I'm supposed to interact with a director, and a director knows what he's supposed to be able to assume about a gaffer. And we're going to encode these kinds of role structures into software, essentially saying that we know what roles people are being hired on to do. In this case, we're going to nest those into teams. Those new teams are going to be nested into a hierarchy. This is going to essentially become, quote, the source code of the organization. And once we have an entire organization, essentially computationally readable, more or less in a JSON format, we can do all sorts of stuff with it. We can introspect on it. We can modulate it. We can hire quickly because we know exactly what role we're hiring for and who we know has those skills. We can onboard people automatically by pointing out who they're supposed to be coordinating with, what kinds of tasks they're supposed to be working on. And we can allow it to adapt. Now, keep in mind that these crowdsourcing workflows struggled because they couldn't adapt. When something changed, they just keep doing the next step. What we allow here is essentially something inspired by version control, where anyone inside of this organization, bottom up or top down, can basically branch the organization, make edits, maybe adding tasks, adding roles, making themselves the boss or something, whatever, and then basically do a pull request to try and merge it back in. What happens is that pull request then gets reviewed by someone who's up the hierarchy. And once it gets merged in, Foundry is able to quickly react and then hire the additional people, update everyone in Slack or wherever it would be to try and update them to the new state of things. So this is essentially a pretty high-level view. I'm not going into too many details, but I want to give you sort of a taste of what this is like. We brought in people who had no experience with crowdsourcing or with on-demand labor. Here we gave them access to a labor pool known as Upwork. You may be familiar with it. It's a sort of online labor market where you can get experts from programmers to marketing, whatever you would really need. The point here, in terms of this evaluation, is an existence proof. Crowdsourcing has never before been able to achieve these kinds of open-ended complex goals. So what I'm going to show is a series of examples where we're now able to do this using this architecture. The first example was the leader here was a medical resident, someone who wanted to create an Android application so that when you're en route to the hospital, they could report what's coming. Turns out hospitals don't know what's showing up until the ambulance arrives at the door, which sounds a little bad. The second example was a group of storytelling game creators. So they were trying to create a card game, sort of like Cards Against Humanity, but for humanity. It's kind of complicated. It was trying to get people to tell stories. You'd get a prompt, everyone would go around, tell a story on that prompt, and then we would vote who would win the best story. So they were designing a game, play testing it, creating assets. And then we worked with Accenture, who wanted to create a workshop portal. So they wanted to actually create something that met enterprise branding standards. And to cut to the chase, what we were able to see was that these end users with no prior experience were able to spin up and lead entire organizations to completion in about 6 weeks. So those goals were all completed in about 6 weeks. And from the moment that they realized they needed a new role to the moment that they had someone in that spot was about 14 minutes on average. So what do I mean? This is something like they built 2 mobile apps, 3 full stack web applications, about 50,000 lines of code, 2 illustrated card decks, about 600 tasks, 550 pull requests, about 3,000 person hours of work. And these things were evaluated by content experts. So the thing starts like this medical resident who knows nothing about building Android apps. And by the end of it, it looks like this. He's built out a front-end team, a back-end team, a UI team, UX, someone who's a HIPAA expert dealing with health privacy issues, a marketing team. This marketing team builds a video advertising this application from nothing to this in about 6 weeks. So they had a fully functional prototype that had been user tested and iterated on. The True Story game, true to their goals, came up with assets. They wrote prompts for each story. So they had a team of poets. They sourced a team of poets to write these prompts for each of these cards. Here's one of them where you're supposed to tell a story about a crush you had, like a romantic crush. This led them to the unusual situation where they had a chief poetry officer in their organization. So consider that. Yeah. We gave each organization something on the order of about 50K. So we fundraised about 50K, and that was end to end. Now, obviously, you can scale that up, you can scale it down. It's sort of a question of how, like each of these organizations had about 30 people. So it was sort of like a small to mid-sized organization. So one of the main points here was that these groups could adapt. So this was a good example where a week before the end, this group decided that they wanted to actually build a companion Android app. So they went from nothing to an entire Android team within a week. So now they could record the stories, upload it to the cloud, and you could play these embarrassing stories again later. Accenture, again, this looks very enterprisey. So they built a portal, had to go through internal rounds of review, react to the changes, and so on. What I want to sort of reflect on here is what are the implications? So one is that we're starting to see this inflection point where organizations might be much more fluid than they are today, where they can be fluidly assembled, reassembled, adapted from globally networked collectives. Now, there's lots of stuff that I think is unanswered here. With more data, can we do more? Can we help suggest organizational configurations that would make sense, for example? Can we support workers and their needs in these kinds of systems, right? What kinds of counter levers do we need to design? Because a worst case situation, someone could use this and be exploitive. And third, there's a lot that economics and co's have to say about this thing called the theory of the firm. Why are people in a firm or outside of a firm? And these kinds of systems really lower the search transaction costs and the bargaining transaction costs, which mean that the sort of nature of firms may shift. Again, who's in and who's out and when. So that's a first thought. I'll hit one more with my time today. This is work again with Melissa Valentine at Stanford and led by Sharon Zhou, who's a PhD student with me there. And I think this one is an interesting question, not just for these digital organizations, but also for the kinds of teams that you work with just today. So Flash organizations and your current organizations work in teams. And you could say, why is that? Why do we all work in teams? And it turns out a lot of people have studied this, and the short version of the answer is that teams are basically the optimal structure when you need things to be ad hoc and flexible. You can imagine that on the other end, when you can specify a recipe, things like crowdsourcing workflows or assembly lines, etc., make sense. But for things like design and engineering, you really need teams to be able to adapt. And the first thing you ask after you have a team, at least if you're managing a team, is how do I do this? Is my team supposed to be flat or hierarchical? Should we be really critical of each other? Should we be supportive? Should we make sure that everyone speaks equally, or should we just sort of have norms and let it all roll out? How do we do this? And these are a lot of decisions. They all get called team structures. Again, think of this as sort of the source code that defines the team and how it behaves, these team structures. And there's a lot of work that basically says, these are the right team structures. Like you can write a New York Times bestseller by basically saying, here's the team structures that you should use. And even in my own area of human-computer interaction, people are theorizing ideal structures and how to make remote teams work well, and we're building systems that try to enforce that. Like you can picture, there are systems that have been built in research literature where there are like little orbs for each person, and the more you talk in the video conference, the more that orb grows, indicating that you're supposed to shut up. Right? These kinds of things, these structures are nudged in these interfaces. And it turns out this is a bad idea. Again, so there's this work in organizational behavior called structural contingency theory. And what it basically asserts is that there is no universally best set of team structures. So if you were to ask me which one should I use, the answer unfortunately appears to be, I don't know, it depends. And this is why it's actually such a hard problem for organizations. If you have the wrong structures, then teams are just going to be dysfunctional. We know this. If it's poorly matched, then the team's going to basically catch on fire and people are going to hate each other and you're not going to achieve your goals. And it turns out that even managers, has anyone here have an MBA? Okay, I'll tread only slightly lightly. Managers are trained and pay for money to be trained in how to make these decisions effectively. And it turns out they're not actually that effective at it. Now, we can blame the MBAs or the people who are teaching the MBAs. I probably shouldn't do that because they're my colleagues. But the problem is that it's just a highly contingent space. It's a very complex space. So it turns out that even a lot of training is really, really hard to do. So again, given my angle, I'm curious whether we can apply sort of a computational lens here. And that is to turn it into sort of a search problem. The system that we've built is called Dream Team. And basically the idea is that your team willingly engages in self-experimentation to try out different team structures and rapidly converge on the structures that work well for you on this task. Structural contingency theory says that it depends on the people and the task. If you change either of them, the structures might need to change. So the basic idea with Dream Team is that the team comes in, they use our system, they're trying some stuff out, and they come out with a set of differently colored structures, because the next team comes in, they have a different set of structures because they're a different set of people or a different kind of task, and everyone comes out with the right thing. We built this thing actually as a Slack bot, so it might look something like this, where you have people come in, and for the purposes of my example, this puzzle robot is going to be the task that they're going to be doing. You can imagine this could be any task that the team is trying to achieve, but for the purpose of our evaluation, I'm just going to introduce this now. They're given a really hard puzzle, inspired by the game Code Games. I don't know if any of you have, Code Words, excuse me. I don't know if any of you have played that. So they're trying to solve this puzzle. There's the end of this round gives feedback to the system. How did they do on this puzzle? Or, how well did the team achieve its quarterly goals or whatever? And the system takes this and makes a suggestion. This time, everyone be super, super cheery. I know this sounds weird, but be really saccharine. Give it a shot. And the team continues. So there are a huge number of possible team structures. This is just a sample of some of the most popular ones in the literature. There's about 400 or so different combinations of these. They range from whether there should be hierarchy to the sort of emotional norms of the group to the how we make decisions and so on. And the basic idea of how Dream Team works is that we start out with essentially neutral norms and structures. We get feedback as to how it's going. The system starts to explore. It changes one thing, and it continues to explore over time to identify the set of structures that are doing best. Underneath the hood, you may be guessing how we're doing this is through a network of bandits. So multi-arm bandits are the kinds of things you see all the time underneath A/B testing. They're trying to identify which kind of setting for each dimension is maximizing the reward. And they do so in such a way to minimize regret, which means that you're not sort of exploring more than you absolutely have to. And the problem is, if you just try this, it's like what happens if I'm a PhD advisor and I tell my PhD advisees like 20 things at once, nothing sticks. Or if your own boss is like giving you 5 different pieces of advice or 15 pieces of advice. So the teams become really quickly overwhelmed because each bandit is independently trying to explore. Yeah. The reward function here, in this case, was the score on the puzzle. But it could be anything, right? It could be the team's subjective feeling of how it's going. It could be the boss's feeling of how it's going. It could be some mix of it. It depends on the task you're trying to achieve. But in the evaluation it's going to be this collaborative, it's called an intellective task, a puzzle. So these teams become overwhelmed. Imagine you're in sort of one setting here, and now you have to change everything. Basically, what happens is that the teams change nothing because it's just too much change for people to absorb at once. So we developed a variant of multi-arm bandits that we call temporally constrained bandits. These temporally constrained bandits basically model how quickly this network can change and also model for each dimension when it's more appropriate to change. And it turns out the literature tells us a lot about when we can do this. So for example, teams are actually most open to change at the midpoint of their progress. So if you just start the team and then start changing things, people don't like it. If you try to change things right as people are sprinting at the end, people don't like it. But around the middle, they're really open to it. And again, individually with certain dimensions like hierarchy, there are certain dimensions that you can change early, certain dimensions you can change late, and certain dimensions you can change all the time. So we're going to throw these parametric models into the temporally constrained bandit. And what it's essentially going to do is redistribute these posterior probabilities of arm selection that we use in Thompson sampling. So without going into too much detail, bandits use this thing called Thompson sampling, which uses all of the past data and then produces essentially a weight, a probability that you should sample each arm next time. So you have arm 1, which might be like no hierarchy, 0.4 probability we should do that next time. Arm 2, Ure's in charge, 0.4 probability. Arm 3, Michael's in charge, bad idea, 0.2 probability. And what we're going to do is we're going to reweight this. We know, for example, that we need to reduce the amount of simultaneous change. So we want to get to a place where we know that Michael's maybe not the best manager, but we're going to hold on to it for a moment, and because we need to try some other things. So we need to basically reduce that exploration by a factor of 4 by essentially sucking those probabilities out of the other arms. There's some math to doing this. It's not actually that complicated, and we want to do this in parallel across all of the network of bandits. So we have all of these different bandits. They each have some probability that they want to change. And we can now enforce essentially a global constraint on the expected number of changes across all the bandits and prioritize which bandits are going to change and when. We call these temporally constrained bandits. And I'm going to make an argument through this evaluation that this actually makes a huge difference. So here's what we're going to do. We're going to bring together workers who have never worked together before off of this Amazon Mechanical Turk platform. You may be familiar with it. It's a place where you can hire basically freelance workers from a US-based or global workforce. We randomize them into about 45 teams. We're going to give them that puzzle task I described to them. That's going to be our dependent variable. That's going to be the performance. How well did they do? And we're going to give them one training round, a baseline round where nothing's happening, and then 10 performance rounds where we're allowing the system to go. And we're trying a few different things. Okay, step 1, MBAs, close your ears. Step 1, option 1, we're having managers try to pick the best set of structures. So between each round, they're given a full list of these structures and they say, pick the ones you want the teams to have, try it. Okay? 2, democracy, essentially. Same information, but given to everyone, and the team collectively decides each round which thing should we be doing. 3, control. Anarchy, basically. No information, right? Just come together and work. So not quite anarchy, just sort of lack of information. And then we have 2 computationally powered groups. One is unconstrained bandits. So these are a network of bandits without the temporal constraints. So there'll be a lot of change. And 5 is the full dream team system, right? Where we have the temporally constrained bandits. And what we see is that we end up with the dream team condition massively outperforming these other ones. So managers, collectively chosen, control, unconstrained bandits all basically do about the same as each other. And Dream Team performs about 40% better. So these teams, just through manipulation of their team structures to be effective, are performing at about 40% better on this intellective puzzle task. How well does this generalize? We don't know yet. We're working with some firms to actually try deploying this inside of actual organizations, on actual teams over longer time periods. But it's a pretty striking first result. So what do we take out of this? 1, okay, why did this happen? It turns out, again, people are risk averse. This is known as prospect theory. Some guys named Kahneman and Tversky got some good awards for this. The point is that people basically don't want to explore very much. So people have a lot of what's known as regret in the technical sense here, where they should have explored more, but the managers would be like, okay, we've tried 3 things so far, 3 rounds, we've tried some stuff. It's pretty good. Okay, let's stop. I see you, just one sec. The bandits explored far more. So maybe an average of about 7 different configurations as opposed to 3 when people were in charge. So the algorithms, unfortunately, if you don't give them any sort of control, they basically overwhelm, they overcompensate. But if you can pay attention to what people are able to sort of absorb at any given point, you find that sweet spot. So there was a question up here, yeah.
Do you make any assumptions about the supply of different types of talent needed to solve a given problem or task? In the sense that if you have a few people who have certain skills that are in demand and they're more over-constrained, so they're not as fungible as...
Right.
This quickly.
Yeah, so this is so the question is about whether you have like constraints on people. This creates, this is essentially the team composition problem. Who do you put on the team given some resource constraints, basically? We have other work that's looking at that. You can view it as some sort of, what we've been thinking about is as again, some sort of essentially optimization problem where there's some cost to moving people between teams, right? There's a cost whenever there's disruption, but then there's also benefits to moving, right? Like maybe you have the high performer on the team, or you're bringing ideas from around different parts of the organization. And we've been developing algorithms that do what we call network rotation, which basically moves people around the collaboration network to try and balance these. So you keep people together when it's valuable to do so, and you move people around when you can. So it's an important question. It's not something at all acknowledged in this particular project because essentially everyone here had equal skill.
Can you say what's the language of team structures? So you say be cheery, be serious. There is one leader. Can you talk about that?
Yeah. So there's a huge literature of this, and basically, yeah. So we used a series of. Let me put it here. These were the ones we used. So it was 5 different dimensions and somewhere between 3 and 5 different values for each dimension, ranging around hierarchy, interaction patterns in terms of like how much volume people have. What was it supposed to be professional or informal? Were we supposed to try and go for crazy ideas, try to agree on things, try to go learn a lot, or just try to make decisions rapidly? And where are we supposed to be encouraging and critical? We got these out of the OB literature, yeah. Right. Yeah, so right. So each value essentially has a string mapped onto it. That's the nudge, right? So here's an example. You basically have to do it in such a way that people will pay attention. This is the one where it says be cheery, right? This says change the value of the feedback norms dimension to encouraging. Now, is this the best user interface for it? I don't know. It was the best one we tried. And it was the best one we tried because it was basically brief, right? You have this trade-off where people just may not pay attention. So in closing, again, we need to think about how are we going to combine voices equitably in the reward feedback, right? Whose voice matters? Is it the team members? Is it the person who's running the team? Is it some sort of automatically observable signal? And how does this thing adapt when membership changes? Can we learn from previous data? Can we use contextual bandits, et cetera, to try and make the adaptation faster? This generally had, converged within about 10 rounds, which, is actually fairly quickly. It was an order of like an hour or so for these teams. But when you have much longer term teams, things might change. So there are many things I'm not going to cover today. Questions of credit. Right? Can we decentralize this question of how much each person deserves in credit for their contributions? This has implications for performance reviews, for author order in academic publications, and other things. But what I would close with is just sort of the higher level area we've been thinking about, is rather than structuring this future of work essentially as algorithms. There's a lot of buzz about like AIs and algorithms and so on. Let's think about ways in which we can computationally infuse the kinds of organizational structures we already have. How can we amplify our ability to get stuff done? Could we create the next major wonder of the world if we effectively harnessed our collaborative abilities and stopped getting in each other's ways? And a final thought. Organizations came about in the Industrial Revolution. Specifically, they came about at the time that railroads evolved. And this was because railroads needed to synchronize timetables across cities. You never had a geographically disparate organization that needed to sync things before. And so they looked around, and they were looking for metaphors for how to do this. And they saw the Industrial Revolution. They saw the metaphor they latched onto was one of mechanisms, so like gears interlocking. And many of the original organizational theorists, Weber and others, basically imagined this as like gears interlocking. We want organizations to work as effectively as like people are gears interlocking, working beautifully together. And in that time, since that's happened, since that metaphor took root in organizations like the ones you're in now, computation went from a dream of Charles Babbage to something on my watch. So what happens if we re-envision the organizations that we work with around a computational metaphor? Computation is reactive, it's reflective, it's data-driven, it's intelligent. What do our organizations look like if we start from that metaphor instead? And that's what we're continuing to push on with our work. So I'll close here. Thanks again to amazing students, amazing colleagues, amazing supporters, amazing questions, and anything else. Thanks.
This was actually super awesome given all the circumstances. Do people have any questions for Michael? Yes, go ahead.
One question. So I'm curious, like why in the experiment the control also performs the manager chosen and democracy, and also like for the manager chosen, how do you choose the manager for a group?
Right. So the question is, why did all of the other conditions do basically the same as each other? Right? Yes. In point of fact, they didn't. It's a little bit. You have to unbury the statistics a little bit. But what's essentially happening when you do the post hoc comparisons between the conditions here, these pairwise differences aren't significant. So essentially, what that means is that there's more variation than there is signal here. If you like really bumped up n, maybe you would see this. Maybe some of them would change order slightly. But more or less, I wouldn't pay attention to the differences within these. Now, you should ask next, why? Why is there no difference here? And that might have something to do with, were we using Stanford MBAs? No, right? If we did, would it do better? Probably, right? I would hope so, right? I don't think any of my salary comes from them because they're a separate school. But probably would do better, right? So it's still happening. Like it's open. In some situations, organizational behavior would predict that these conditions would do better. In these conditions, they didn't. In this particular study, the manager was chosen as a member of the group. So they could have chosen poorly, but it was basically, average quality managers in that sense. Let's work backward forward. So in the green.
Hire skilled workers to participate in crowdsourcing and the Splash organization stuff. Because traditionally, in simple tasks, people have no English, for instance. That's the part. But if I want to have a Flash organization and get 5 vision engineers, how do you incentivize those to participate?
Right. So the question is, how do you incentivize the 10xers or the 100xers or whatever to actually participate in this ecosystem? I have 2 answers. One, you have to make it actually interesting, right? Part of this Flash organization's work was a reaction to everything being this microtask labeling of images. No one wants to do that. You don't want to do that because it's it's boring, right? It's not intellectually fulfilling. And by trying to move toward these more integrated, design, engineering, innovation kinds of goals, I think you start to attract some people. 2, if you want to get it, I think you have to fix reputation. I think this is probably the big, Nobel-worthy problem in online marketplaces right now. I call it sort of the Yelp problem, where everyone's 4.5 stars. And because everyone's 4.5 stars, you have the variation is so high, within that, you can't get any signal. So I've hired people off of Upwork who appear to be really, really highly rated, like someone who's a visual designer, and it was terrible. And then someone with the exact same rating was really great. And I think John Horton, who's a labor economist at NYU, has demonstrated that what's happening is reputation inflation. So if you look at the average ratings on these platforms over time, they're sort of doing this. And the reason for it, if you reflect on the last time you took a Lyft or an Uber or anything like this, is that they're like, give me 5 stars, yeah? Right? So what's the cost to you? None. It's externalized, right? What's the cost to them if they get a low rating? They get booted off the platform. So over time, people are giving everyone 5 stars, and the ratings become meaningless. I think you need to solve reputation as a prerequisite to getting actual experts. Because right now, the actual experts are going to look just like the people who are not worth hiring. Sorry, cut me off whenever.
Let's do last question and then move on.
Sure.
Interesting thought, thank you. I'm wondering if there's a way to actually give an upper bound to what sort of problems can be solved given a particular platform, right?
A New York Times bestseller, right? If I give a prior bestseller author or a bunch of them together, right, it's still not 100% clear that I'll get another New York Times bestseller, right? And the same is true for like if I throw unlimited resources at an engineering team to create a video platform like YouTube, right? So is there a way that you could tell me that given Amazon Mechanical Turk, you cannot get a best-selling novel?
Right. So the question was, are there sort of impossibility guarantees, right? Can we say, here's the maximum that's feasible with this kind of structure? We can give sort of on average estimates, where on average this thing's not going to be as good. You can't argue that it can't exist, because honestly, collaboration structures can be very flexible, and people find ways around things. So on average, given certain kinds of people, yes, you can make predictions. But the New York Times bestseller example is interesting because we know that with cultural artifacts, actually a lot of the outcome is endogenous, meaning that like early variation ends up sort of cascading into becoming bestseller or sort of not bestseller status. Something we're studying now is how much of the thing that comes out of the team is actually random, right? So if you reran the same team, what we're doing now is we're rerunning the exact same team, but we're blinding them to the fact that they've worked with that team before. So imagine something where you all have different pseudonyms and you don't realize that you're all the same team, and we can verify that this because we ask you to guess which two teams were the same and you can't guess. Do you actually produce something of equivalent quality, or do you end up way better or way worse? Or likewise, do you like get into fights one time but not the other time? Or is it just sort of guaranteed that this set of people, no matter how many times you were to get together, are going to catch on fire? Those are two sources of variation, right? They're sort of within the group, and then once the group has produced whatever it's going to do, and this is what makes it hard. But that's why prediction's also a fun problem. When we can get signals, we leverage what we can.
Great. So thank you, Michael.